Welcome to a lesson with Dr. Powell. In the last video, we discussed the idea of what it means for a matrix to leave a subspace still the same subspace so that it would be invariant under the action of that matrix. Um, so what we're going to be doing is we're going to be considering a matrix. So here's an example. And we're going to be looking for subspaces such that polynomial scalars, so polynomials with this matrix A representing the action of x, don't move us out of the subspace. So we're going to be looking for subspaces. Okay, so how are we going to do this? Well, we are going to be looking at some operations that we can do on this matrix here. So what is this? This is like the zero matrix because this is basically this statement. If we set this equal to 0, that's a statement that xi is the same as a. So with x is just down the diagonal, that, and then subtracting off the matrix A, that's going to be the zero matrix. Okay, it's saying that they're the same. All right. So I'm going to be doing some operations on this. We're only going to focus on column operations. And we're going to do them up until a point, up until it's pretty clear that row operations could finish us off to take us to a diagonal matrix. So we're not going to actually go all the way to the diagonal matrix. There's no need. But in fact, what we need happens before we actually get to the diagonal right here. But in the diagonal itself, let's just look at what we're seeing here in a diagonal matrix with the zeros over here and over here. Notice that if you multiply in this case, a tuple, like a vector, but the coefficients are polynomials, and polynomials themselves, like polynomial scalars, are not invertible, so you can't really think of it as a vector space, but we can call it a module. And linear transformations represented by matrices, we usually don't call them linear transformations in this case. You might call them module homomorphisms if you want a technical word. In fact, I'll write that down if you want something here. So because we're considering our entries are polynomials, and it's the same basic ideas. You're just throwing out the case that you can divide by the scalars. That's about it. But in this case, these linear transformations are really, give them a name here to be technical. We'll call them homomorphisms. And you can even call them Rx module homomorphisms if you want a name for them. But really, they're just these maps represented by matrices the same way as what we're doing before with vector spaces. Okay, so if you consider a diagonal matrix like this, think about what it does if you input, thinking of a column interpretation for a matrix function. If you input like 1, 0, 0 into this, what are you going to get out? Well, you're going to get 1, 0, 0 out again, multiplied by whatever is up here. And in fact, if you put in any Rx, multiple of this, any polynomial in here, it's just going to be that times a polynomial. I mean, we're going to get, in fact, it's going to, basically what it does is it fixes or leaves invariant. I mean, it actually, technically speaking, you're taking all these polynomials and you're multiplying by something. So it's leaving the subspace kind of invariant, but not really. I mean, it's like it's staying within it. It's staying within the Rx span of this. You're not going to get out of this. You're going to have new multiples of things in here, but you're going to stay in here. That's not exactly what we want, especially since we're now dealing with this funny module thing. But we want to focus on R3. What's the, we want to get to here. This is where we want to be. We want to fix subspaces in R3. Okay, this is a start. This is actually going to give us some valuable information as we go, except we don't even need to get all the way to the diagonal to do this. In fact, we can just do this in a few simple steps. So, but we need a little bit of commentary as we go to kind of fill it out as we're starting to look at this. just to kind of get an idea. So that's what we're going to be doing in the next videos that will follow this one. Thanks for watching.